All right, good morning, everybody. Welcome. We made it. Last class, last lecture. So a couple of administrative things. First of all, I want to encourage everybody to fill out your SRIs, your student evaluations of instructor. The department and the university really value those, so I appreciate it if you take some time, put some thought into them. Sometimes it's easy to feel certain feelings about a course and transfer them on to the instructor, whether those are good or bad. So I want you to really try and take some time and think about your answers to the questions. And be honest, I'm not asking for automatic good evaluations. I'm just asking for thoughtful, kind evaluations. But yeah, those are important, so please take some time to do those. I also will have office hours as regular today and then also next week. So our exam is Sunday evening, not this upcoming Sunday, but the following Sunday. So all next week there's no class, but I'll still have office hours like normal, so Monday and Thursday. And also still available for one-on-one meetings if you want to schedule an appointment. I'm happy to meet on your time. Okay, I think that's all the administrative stuff. Test 4 scores are out. We're working on getting test 5 to you as soon as possible. That's over half graded already, so hopefully we'll be able to get that to you as soon as possible, but I don't want to give a hard deadline because we're doing our best. Doing our best on those is what I'll say. Okay, let's get to this warm-up question. So I have the set 1, 2, 3, 4, 5, 6, 8, 12, and A or B if A divides B. I'm going to draw out the Hasse diagram. So let's see. Let's start with 1. Draw it somewhere reasonable. And then 1 divides 2. So I need an arrow, or I need a line going up from 1 to 2. No arrows, though, in my Hasse diagram. And now the question is there anything else in my set that 1 divides but nothing else divides? Yeah, 3, right? So 3 is also going to go above 1. And 1 does divide 4, but 2 also divides 4, so I want my 4 to come above my 2. And now I know that 2 divides 4. I also know that 1 divides 4 because of transitivity. So for Hasse diagrams, I don't have to draw that. And next I have 6. 6 is divisible by both 2 and 3. Then I have 8. 8 divisible by 4, which is divisible by 2, which is divisible by 1, so I get all of those chains. And then I have 12, last but not least, divisible by both 4 and 6. I get a diagram that looks like this. And we can ask some questions about this diagram. Like, what are maximal elements? What is the maximum element? What are minimal elements? What's the minimal element? Okay. Answers to any of these, what do we think? Missing a minimum, have two minimals. Oh, missing a maximum. Maximal, maximum, minimal. Yes, sorry. Now I understand. Minimum. What is minimum element? Sorry about that. What are maximal elements? What is maximum element? What are minimal elements? What is minimum element? Okay. No maximum. Good. Start there. I like that one. All right, so remember, a maximum element towers above everything else. There's nothing below it. But here I have 8 and 12. Nothing is bigger than 8. And also nothing is bigger than 12. So I don't have one singular maximum element. But both 8 and 12 are maximal because nothing is bigger than them. They both satisfy nothing is bigger than them. Minimal elements, I only have one, and it's 1 because that is also the minimum element. Good job. Questions about any of these? What is, ooh, this is a good question. Excellent. What is the least upper bound of 4 and 2? Of 2 and 4, I guess, but there's symmetry involved. So let's recall the definition of least upper bound. It's got to be an upper bound, which means it has to be bigger than both 4 and 2. And at the same time, it has to be the smallest one with that property. So which numbers in this Hasse diagram are bigger than both 4 and 2? What are the upper bounds? For 2 and 4. Eight definitely an upper bound. 4 divides 8 and 2 divides 8. 12 definitely an upper bound. 4 divides 12 and 2 divides 12. Are there any other numbers that both 2 and 4 divide? Also 4. Right? 4 is an upper bound because 2 divides 4 and 4 divides 4. Both of these are true. So this is my list of upper bounds. Which one of these is my least upper bound? 4. So that makes 4 the least upper bound for 2 and 4. Right, it's a good question. I do want to also point out that We can talk about lower bounds for more than two things. So I could say, like, what is the least upper bound for 2, 3, and 6? No reason, it just has to be two things. Could be a whole set of things. And so what is the least upper bound of 2, 3, and 6? 6. Good. All of these things, 6, all of these things divide 6. So 6 is above all of these things. It doesn't have to be strictly above because everything has a loop back to itself. Good. One more thing I wanted to mention about partial orderings. If A is a set and curly less than or equal to is a partial ordering, on A, then the set together with the partial ordering is called a partially ordered set. Which we often abbreviate to a PO set. And we don't even put periods in. It's not an abbreviation. It's just partially ordered becomes PO set. PO set. So you might see that word that means partially ordered set, which means a set with a partial ordering. And it's just a different focus. Right, if we look at this Hasse diagram, technically this is a Hasse diagram for the relation R. But I mean, it's very easy to think about the set A being ordered. Right? It's an ordering on A. Well, that's one way of thinking about it. It's also a relation R just on the set A. So, depending on whether you want to focus on the set, in which case it's a PO set, a partially ordered set, or the relation, which is a partial ordering, you can refer to both sort of separately. So, wanted to mention both. Okay. So let's go back to equivalence relations. So last time we talked about how, so let's just review equivalence relations. Are reflexive, symmetric, and transitive. And we talked about what their digraph diagrams look like, right? There are a bunch of groups of vertices, all with as many edges as possible, and then the different groups are separate. And we talked about how that related to partitions. Every equivalence relation induces a partition and vice versa. Meaning every partition is associated with an equivalence relation. So there's one particular equivalence relation I want to look at. For any n, A related to B if A and B have the same remainder divided by n is an equivalence relation. So let me prove that. I need to show three things. I need to show that this equivalence relation is reflexive, symmetric, and transitive. So I'll say R is reflexive because if I have any y and I divide by n, I get the same remainder as if I divide by y. If I divide y by n. Y divided by n has the same remainder. B remainder as itself. So reflexive should make sense. If I divide y by n, I get the same remainder as dividing y by n, just one thing. Why is R symmetric? So if I have an arrow from A to B, that means A and B have the same remainder when divided by n. Why am I symmetric? I don't want y over y. Y divided by y is always going to be 1. I'm always dividing by n here. Yeah, right. If a over n has the same remainder as b over n, that's what it means to have an arrow from A to B, then b over n has the same remainder as a over n. Right? It's silly to write it out this way, but we're writing it out to be thorough. We're writing it out to give a full proof. If a over n has the same remainder as b over n, then b over n must have the same remainder as a over n. Right? The remainder of a over n is some c, and the remainder of b over n is some c. That's still true even if you reverse the order of things. So the slightly trickier one is transitive. Let's show that this relation is transitive. So R is transitive because if I'll do sub bullets, if A is equal to P1n plus Q1 with 0 less than or equal to Q1 strictly smaller than n. So we saw back when we did Euclidean algorithm stuff, we can always write our integers like this, and Q1 is the remainder. B is equal to P2 n plus Q2. Again, with 0 less than or equal to Q2, strictly smaller than n. And C is P3 n plus Q3, less than or equal to Q3 less than n. then, oops, I'm running off the bottom of the page here. ARB means what in this context? Q1 equals Q2. Really good. ARB means A and B have the same remainder when divided by n. The remainders here are my Q1, Q2, 3, Q1, Q2, Q3. So ARB means Q1 is equal to Q2. And BRC means what? Q2 equals Q3. Good. So if ARB and BRC, then Q1 is equal to Q2 is equal to Q3. So Q1 is equal to Q3 and ARC. So if I have ARB, that means Q1 is the same as Q2. If I also have BRC, that means Q2 is the same as Q3. So ARB and BRC means Q1 and Q3 have to be the same. That means that ARC. And that's what I need for transitive. Okay. So R is reflexive, symmetric, and transitive, and therefore an equivalence relation. Okay. Let me do an example. What are the equivalence classes of the integers so we call this particular relation the modulo relation. Modulo, let's say 5. So I'm looking for the sets of numbers that have the same remainder when divided by 5. So what is one of my sets of integers? One, 6, 11, yeah, good. So one of them contains 1, 6, 11, 16. All of these numbers have remainder 1 when I divide by 5. But I suspiciously left some space because I am talking about all integers, not just the positive ones. So what else belongs in this set? Yeah, how do we make negative numbers work? So let's think about it. What negative number can I write as some multiple of 5 plus 1. So I want z is equal to some multiple of 5 plus 1. Well, if I want a negative number, let's make this a negative 1. What number falls into the same class? Yeah, this is going to be minus 4. I get a minus 4 here. And if I put a minus 2 here, then that's going to give me a minus 9. And if I put a minus 3 here, it's going to give me a minus 14. And I get to go infinitely in both directions. So this corresponds to 5 times 0. Do 2 colors. 5 times 0 plus 1. And this is 5 times 1 plus 1. And this is 5 times 2 plus 1. The coloring has gotten screwed up. And I can keep going in the opposite direction as well. This is 5 times negative 1 plus 1. And 5 times negative 2 plus 1. So this is the set of all things that are one off from a multiple of 5, whether positive or negative. Okay, and this is one of my sets. What's another set? Another one of my equivalence classes. Yep, so I'm going to get the ones that are 2 off. So I get 2, 7, 12, 17. But what else do I get? Negative 3, negative 8, negative 13, good. Because negative 3 is minus 1 times 5 plus 2. This is 0 times 5 plus 2. This is minus 1 times 5 plus 2. Okay, so I got a couple more sets. Here's 2 of them. What are my other equivalence classes? Rough morning, huh? I mean, it is the end of the semester. There we go. Somebody's helping me out. 3, 8, 13, 18, and so on. But then I'm going to go negative. Good. So that's going to include minus 2, minus 7, minus 12. Okay, I'm up to 3 equivalence classes. Not done yet. Good, then we can do the 4s. So 4, 9, 14, 19. And this extends the other way. We get minus 1, minus 6, minus 11. And are we done? Do we have them all? Yeah, good. We also need the multiples of 5. Important not to forget this one. So we have 0. So this is 5 times 0 plus 0. 5 times 1 plus 0. 5 times 2 plus 0. And so on. 15. Okay. And now are we done? Yes. How do we know that we're done now? There are no more remainders. Good. We're also back where we started. This is the point I want to get at. Every integer shows up in one of these 5 classes. Every integer appears in, maybe I'll add exactly, one of these 5 classes. And that's what we want from a partition. Equivalence relations are supposed to be partitions. Every number is supposed to show up exactly once in one of these sets. Okay, but there is one thing about these sets. There are a lot to write out every time. And so I have some notation that means the same thing. This is the equivalence class associated with 1. So I'm going to write this. This is the equivalence class associated with 2, the equivalence class associated with 3, the equivalence class associated with 4, and the equivalence class associated with 0. So I picked out the elements 1, 2, 3, 4, and 0. And these are called representatives of their equivalence class. And I put the representative in square brackets, and this means the same thing as this whole set. So I can talk about 1 belongs to square bracket 1 and square bracket, because that's a set of numbers. So I can say things like 1 belongs to square bracket 1, and 6 belongs to square bracket 1, and minus 7 does not belong to square bracket 1, and so on. Okay. And so this representative notation works for any equivalence class. So for any equivalence class, or for any equivalence relation, any equivalence relation, I'll call it similar. This is the symbol we use for equivalence relations on a set A. For any x in A, brackets x is the set of y in A such that x is similar to y. This is the equivalence relation equal to the set of elements equivalent to x. Okay. So let's learn some things about this. If x is not equivalent to y, then what do I know about the equivalence class of X and the equivalence class of Y. Think back to examples here. So 2 is not equivalent to 3. What do we know about these sets? Yeah, right there, disjoint. This is equal to the empty set. If we're not equivalent, then nothing, we don't overlap at all. We're completely disjoint because equivalence relationships induce partitions. These are two different sets in a partition. They can't overlap at all. And so the other side of that is if X is related to Y, then what can we say about the equivalence classes of X and Y? They're equal, right? These are equal, and they're equal as sets. So that means that X is a subset. The equivalence class of X is a subset of the equivalence class of Y. And the equivalence class of Y is a subset of the equivalence class of X. Right? That's what we mean when we say two sets are equal. And that's what equality means here. So we can pick any representative to put in our square brackets. In our example, in the integers modulo 5, that was our example, which, by the way, we typically draw or write like this, denote like this. Just a little 5 down there means dealing with those. I can say things like square brackets 1 is equal to square brackets minus 4 is equal to square brackets 6. I can pick any representative I want out of my equivalence classes. And actually, typically, when we're dealing with the integers modulo a certain number, we don't write the square brackets. This means the exact same thing as 1 minus 4 and 6. These are not equal, they are equivalent. So I add an extra line. And then at the end I can add mod, short for modulo 5. These two things mean the same. They are just different notations for expressing the same idea of equivalence classes and which equivalence classes are the same. Okay, let's take 2 minutes. We'll come back 9:13. Go ahead, stretch, grab a drink, snack, whatever you need. Come back in 2 minutes. We'll talk more about modular arithmetic. I'm also going to go grab some water. Okay, let's gather back, recenter, refocus, keep going, and we'll wrap up today. So I want to talk about what we can do with these integers modulo 5. What happens if x is any number belonging to the equivalence class mod 1 and y is any number belonging to the equivalence class mod 2? Then that means x is equal to some q1 times 5 plus 1. That's what it means to be in this equivalence class. And y is equal to some q2 times 5 plus 2. So which equivalence class does x plus y belong to? If I add these two numbers, I want to pick one of my 5 equivalence classes. So I want to pick brackets 1, brackets 2, brackets 3, brackets 4, or brackets 0. Yeah, this is an element of brackets 3. Because, let's see why, x plus y equals q1 times 5 plus 1, that's what x is equal to, plus q2 times 5 plus 2, that's what y is equal to. And I can rearrange this as q1 plus q2 times 5 plus 3. So the remainder, when I divide x plus y by 5, I'm going to have 3 leftovers. 1 leftover from when I divide x by 5, 2 leftovers from when I divide y by 5. Combine them together, I get 3 total leftovers. And I can say more than that. X times y is also going to belong to one equivalence class. Let's see which one it is. Let's multiply these out. X times y belongs to what? So this is q1 times 5 plus 1 times q2 times 5 plus 2. This is equal to, multiply this out, so q1 times q2 times 25 plus 2 times q1 times 5 plus 1 times q2 times 5 plus 1 times 2. And if I want to pull out a multiple of 5, what do I want to say? This is equal to something times 5 plus something. What are my somethings? If I factor a 5 out of this term, what do I get? Yeah, good. So I'm going to get 5 Q1, Q2. I'm going to get, factor out of 5, I get 2 Q1s left over. Factor out of 5, I'm going to get 1 Q2 left over. And I can't factor a 5 out of this 2. So I have a 2 left over at the end. And so if I go back and finish this statement, what equivalence class is x times y in 2? Good. And remember, it does not matter which one of these I'm picking. Any element x that's in the equivalence class of 1, any equivalence class, any element y of equivalence class 2, if I add them, I get 3, and if I multiply them, I get 2. So is it the greater equivalence class? Let's see. Let's try and do this in general. What equivalence class? So if, let's actually just ask the question, what is equivalence class of x times equivalence class of y? So this is going to be q1 times n. I don't even have to be, it doesn't have to be mod 5 anymore. I'm just going to do q1n plus x times q2n plus y. Multiply these together, I'm going to get q1 q2 n squared plus y times q1 n plus x times q2 n plus x times y. And I want to factor out as many n's as possible. So this is going to be q1 q2 n plus y q1 plus x q2 all times an n with an xy left over. So that means what is x times y? What is my remainder here? The set x times y, the equivalence class of whatever x times y is. So I want to point out, brackets x and brackets y are sets. In general, we cannot add sets, and we cannot multiply sets. We can take Cartesian products, but that's different. That's not what I'm doing here. I am defining addition and multiplication of these equivalence classes. Because if I take any element in brackets x and multiply it by any element of brackets y, I end up with an element in brackets xy. And because that works for any element, we say it works for these partition classes as well, these equivalence classes as well. Does not work for every set. We're defining it for this particular case. And this gives us what we call modular arithmetic. So this lets me write things like 7 plus 11 is equivalent to 3 mod 5. And what this means is the equivalence class of 7 plus the equivalence class of 11 is equal to the equivalence class 18 And remember what I said, there's nothing special about 18. I can pick any element out of this equivalence class that I want. What's an easier thing to use to represent the equivalence class of 18? That's the same as the equivalence class of 3 when I'm talking about the integers mod 5. Similarly, 7 times 11 is equivalent to 2 mod 5. And this is because the equivalence class of 7 times the equivalence class of 11 is the equivalence class 77, and 2 happens to be in the same equivalence class, mod 5. So rather than use 77 as a representative, I could also use 2. In fact, I could do this another way. I could say that equivalence class of 7 plus equivalence class of 11, I could pick different representatives from these equivalence classes. I could say that this is equivalent to, instead of using 7 mod 5, I'm going to use 2 mod 5. Instead of 11 mod 5, I'm going to use 1 mod 5. And that's equal to 3. Seven times 11 is equal to 2 times 1 equal to 2. So I can either do the arithmetic first and then take the remainder, or I can take the remainders first and multiply together, and I'm getting the same answer. So this is modular arithmetic. We can add and multiply numbers, mod 5. So let's do some examples. Let's do 8 plus 9 is equivalent to what? Mod 7. And let's do 3 times 8 is equivalent to what? Mod 4. And let's do 9 plus, let's do 9 times minus 2. It's equivalent to what? Mod 7. And one last one. Let's do 4 minus 6 is equivalent to what? Mod 3. Okay, so let's see if we can fill in some of these. Let's start with this first one. What is 8 plus 9 mod 7? Yeah, so 8 plus 9, we could do this in 2 different ways. 8 plus 9 is 17. 17, when I divide by 7, I get a remainder of 3. Or I can say 8 is 1 mod 7. 9 is 2 mod 7. 1 plus 2 is 3 mod 7. Again, 2 ways of doing 3 times 8. 3 times 8 can be 24. Take a remainder when I divide by 4 and get 0. Or I can point out that 8 is in the same equivalence class as 0. So this is just 3 times 0, which gives me 0. So 9 times minus 2 gives me minus 18. I can try and work out what equivalence class minus 18 is in. But I don't know about you. I always have a harder time with the negative numbers, especially with something like 7. So when I do this calculation, instead of minus 2, I'm going to do 9 times 5. 9 times 5 is 45. I know that one. What's 45 mod 7? 45 mod 7, well, I know 7 times 5 is 35. So I get a remainder of 10. But I can do even better. I can do 7 times 6 is 42. I can get a remainder of 3. But it is true that 9 times negative 2 is equivalent to 10 mod 7. It's also true that 9 times 2 is equivalent to minus 18 mod 7. So I can put a 3 here, I can put a 10 here. Typically, when we do modular arithmetic, we like to use the numbers between 0 and n minus 1. So I'll put that here. Doing modular arithmetic. Best to have answer between 0 and n minus 1. Those are typically the representatives we use for the equivalence classes. So 4 minus 6, that's going to give me minus 2, which is the same equivalence class as 1 mod 3. I can also think of this as 4 minus 0 mod 3, because 6 is equivalent to 0 mod 3. I can do all of these calculations. Questions? One more topic I want to talk about on these. Okay. So we can think of modular arithmetic, either addition or multiplication, as a binary function. I cannot spell today. Arithmetic. Metic. I did an A. I did an E here, so I'll do an A here. One of those has to be right. As a binary function on the set 0, 1, all the way up to n minus 1. So I can think of plus, fill in this table, 0, 1, 2, 3, 4. So this is mod 5 plus mod 5. 0, 1, 2, 3, 4. I can fill this in. 0 plus 0 mod 4 is 0. 0 plus 1 is 1. 0 plus 2 is 2. 0 plus 3 is 3. 0 plus 4 is 4. 1 plus 0 is 1. 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3 is 4. 1 plus 4 is 0. I want this to be a closed binary function. So all of my outputs have to be between 0 and 4 as well. And then I get 2, 3, 4, 0, 1. 3, 4, 0, 1, 2. 4, 0, 1, 2, 3. And fortunately, addition is symmetric, or is symmetric, so that is commutative. Sorry, that's the one I'm looking for. Symmetric is for relations, commutative is for functions. I don't have to worry about which one of these numbers comes first and which comes second, because it's commutative. So I can also fill in one of these charts for times. This is the times tables, but for modular arithmetic. This is the times tables mod 5. 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. So 0 times 0 is 0. And in fact, 0 times anything is 0. One times 1 is 1. 1 times 2 is 2. 3, 4. 2 times 1 is 2. 2 times 2 is 4. 2 times 3 is 6. Mod 5 is 1. 2 times 4 is 8. Mod 5 is 3. 3 times 1, 3. 3 times 2, 1. 3 times 3 is 9. Mod 5 is 4. 3 times 4 is 12. Mod 5 is 2. 4 times 1, 4. 4 times 2 is 8. Mod 5 is 3. 4 times 3 is 12. Mod 5 is 2. 4 times 4 is 16. Mod 5 is 1. Okay, so I filled in these two tables. And if you like patterns, which if you're a human, you probably like patterns, you'll notice that these two tables have lots of patterns in them. So if you like this kind of thing, then you really want to take a number theory course. You can dive deep into all of these patterns. Number theory, really big on modular arithmetic and all the things you can do. But one thing I want to focus on, one of the patterns I want to focus on, is that every row in this multiplication column has, except for the zeros, 0 row and column, has a 1 in it. There's exactly 1 1 in it. So what this means is when I'm dealing with numbers mod 5, there's always something I can multiply by your number to get 1. Now, if we were talking about fractions, that would be a reciprocal. Right, so remember, the reciprocal of x is 1 over x, because x times 1 over x is equal to 1. I can also talk about inverses mod 5. So x is the inverse of y mod n if x times y is equivalent to 1 mod n. So what is the inverse of 3 mod 5? Two mod 5, the equivalence class 2, from which I can select any representative, and so I'll select 2, is the inverse of 3 mod 5. Okay. Let's talk about this more generally. What is the inverse of 43 mod 117? This is a harder question. 74. Let's check. Let's see. We got to guess. 43 times 74. 3 times 4 is 12. Add 1 up here. 4 times 4 is 16. Carry the 1, 17. 7 times 3 is 21. Carry the 2. 28 gives me 30. So I get 3182. So 43 times 117, times 74 is equivalent to 3182 mod 117. And now I need the remainder when 3182 is divided by 117. So I can't quite get 2 copies into 318. That would give me 200. Oh, I can get 2 copies. I can't quite get 3 copies, but I can get 2 copies. So this gives me 234. Subtract 8 minus 4 is 4. 31 minus 23 is 8. So 842. How many times does this go into 842? Gonna guess 7. 7 seems right. So 7 times 7 is 49. Carry the 4. 7 times 1 is 7 plus the 4 gives me an 11. Carry the 1. 7, 8. I'm off the bottom of the page. So it looks like I'm getting a remainder of 123. Yeah, 23. So no dice. 74, I mean, fine guess. Didn't work out. 31, could be 31. Not going through all that again. The point is, I don't want to guess. I want a surefire way of finding the answer. And so the surefire way of finding the answer is something we have already talked about. And it is the Euclidean algorithm. So, in particular, the extended Euclidean algorithm. First, I want the GCD of 117 and 43. Okay. So let's remember how we do this. I want to say, so how do we start a Euclidean algorithm? What's our first step? 117 and 43. Good. 117 equals 43 times some amount with some remainder. So 43, double that, we get 86. But I can't get another one of those in there, so I want 2 times 43, that's 86. Plus, how many more do I need to get up here? 31. Okay. And now 43 is 1 times 31 plus 12. 31, right? All coming back now, how we do this. 31 is, we can get 2 copies of 12 in there. plus that's 24, so I need 7 left over. And now 12 is 1 times 7 plus 5. And 7 is 1 times 5 plus 2. And 5 is 2 times 2 plus 1. And technically I have one more step. Technically I should say that 2 is equal to 2 times 1 plus 0. But I ran out of room. So just imagine that's on the next page. Okay. And now, because the GCD of these two numbers is 1, I know that I can find an expression that looks like 1 is equal to 117 times one number plus 43 times another number. This is what I want to do next. Let's see why. So I want to do the reverse Euclidean algorithm. So 1 is equal to 5 minus 2 times 2, which is equal to replace 2 with 7 minus 5. 5 is minus 2 times 7 minus 5. So this is equal to positive 3 copies of 5 minus 2 copies of 7. Now I replace 5 with 12 minus 7. Minus 2 times 7, so this is going to give me 3 copies of 12 and 5 copies of 7. And now I replace 7 with 31 minus 2 times 12. To get 10 more copies of 12, so 13 times 12 minus 5 times 31. And now I replace 12 with 43 minus 31. 13 times 43 minus 31 minus 5 times 31. So I'm going to get 18 copies of 31 and 13 copies of 43. And now I replace 31 with 117 minus 2 times 43. (117 minus 2 times 43). Really trying to squeeze everything in here. To get 18 times 2 is 36. 36 plus 13 gives me 49 copies of 43. Minus 18 copies of 117. And this is equal to 1. And so what I know is that 1 is equal to 49 times 43 minus 18 times 117, if I did my reverse Euclidean algorithm correctly. And if I look at this equation modulo 117, this becomes the equivalence class 1 is equal to the equivalence class 49 times the equivalence class 43 minus the equivalence class 18 times the equivalence class 0. And so this tells me that the inverse of 43 mod 117 is 49. 43 times 49 is how I get 1 mod 117. So we use the Euclidean algorithm to get us our inverses. Mod a number like that. Okay, I'm a little bit over time. Sorry for that. Thank you, everyone. Thank you for the whole course. Like I said, I'll have office hours today. I'll have office hours this week, but that's it for lectures. That's all the material. Got a little bit over a week to prepare for the final exam. I'm here to help you for that. There's also a final exam review session that you received an email about. There's also details about that on UMLearn. So good luck. Let me know what help I can provide, and I'll see you in office hours, or I'll see you some other time. Bye, friends. So sad. All right, I'll stop the recording here.